Hello everybody, welcome to another episode of Math-321. We're going to continue and finish up Investigation 24 today, and then we'll start into Investigation 25. Okay, so this is a summary of what we learned last time. We had definition 24.2. So let n be an integer with n greater than or equal to 3. The dihedral group of order 2n is the group of symmetries of a regular n-gon. So for example, over here I have the regular triangle, and that would correspond to the dihedral group D3. Okay, and then the notation for it is here. So activity 24.3, we learned that we can write all of the elements of Dn as the following list. So starting with the identity, and then that first rotation that is the smallest counterclockwise rotation. And then all of the other rotations, just repeating that counterclockwise rotation. And then you can take all of those same elements, and if you give them a flip over a vertical line at the very end, that will make all of the other elements of the dihedral group. So here in D3 we have I, we have capital R squared, little r, capital R, and then little r, capital R squared, and that is the entire dihedral group of order 6. And then in activity 24.4, we learned that we can swap the order of little r and big R if we change the exponent on big R to be negative. Okay, so let's get into what's left in this investigation. Okay, so generators and relations. So definition 24.5, we say that a subset S of a group G generates G if every element in G can be written as a finite product of the elements of S, or as a finite sum of if the group operation is written additively. The elements of S are called the generators of G. So for example, not for examples. So for example, that set of capital R, the counterclockwise rotation, and little r, the flip over the vertical line, that generates D3, the group of symmetries of the triangle. Okay, so the structure of G is determined by not only what the generators of the group are, but also by how the generators interact with each other. So this wasn't really an issue when we were talking about cyclic groups, because in cyclic groups there's only one generator. But now that we're talking about more than one generator, we have to think about how those generators are going to interact with each other. So an equation that describes the relationship between powers and products of generators is called a relation. And so for example, in D4, which would be the symmetries of the square, in D4 we have the following relations. So we would have little r squared is the identity. So if you do reflection twice, that's the identity. Big R4 equals the identity as well. So if you would do the rotation 4 times, that'll take you back to where you started. And then we have also this equation, which was something that we derived last time, that's true in all of the dihedral groups. So actually all of the other relations amongst the powers and products of little r and big R in D4, they can all be derived from just those 3 relations, which is kind of interesting. So that leads us to the next definition. So group presentations. So for a group G, the pair consisting of the generating subset S together with the relations necessary to describe all interactions among S, that is called a presentation of G. So the notation for the presentation, you use these little angle brackets, and then you just put a list of the generators, and then you put this vertical line standing for such that, and then you put a list of the relations. So it's basically like you're saying you're going to take all of the products and powers and combinations of those generators such that the relations are true. That's basically the meaning of the notation. So for example, if we look at D4, which again is the symmetries of the square, we can write D4 as little r big R such that little r squared is I, big R to the 4th is I, and then we also have this last relation here. Similarly, oh, this is a typo here. Sorry, this is supposed to be double Z. So Z4, the cyclic group of 4 elements, can be written as the generator of 1, or the congruent class of 1, such that 4 times the congruence class of 1 equals 0. Okay, so just a word to mention about existence and non-uniqueness. So we're not going to prove this, but every group has a presentation, at least one presentation. And furthermore, presentations, they're not necessarily unique. So for example, there are other ways to write D4. So we could also write it, so using the same little r and big R as before, but if we make this exponent here -2, and if we make this one -4, that's another presentation of the group that would give rise to the same group. And another example here with Z4, the cyclic group Z4, we could have used the element 3 as the generator instead of 1. So that is not a unique presentation either. And it is actually extremely difficult to determine whether two presentations represent the same group. Okay, so now let's do activity 24.6. So go ahead and pause the show and try this activity, and then we will go over it. Okay, so let's go over part A here. So part A is actually like deceptively difficult because we're looking at these two elements A and B, and you could really combine those two elements in any way. So what you need is you need all the products and powers and products of powers of A and B, and that's obviously infinitely many of them. Like for example, you could have A to the 100, you could have B to the 10 times A to the 10 times A to the 5 times B to the 2. I mean, you could combine the A's there, but other than that, we don't know if the group is abelian, so we could have things like AB, 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 and etc. So it's really important that we have the relations that are listed there in the group presentation to help prevent this insanity. And I don't know if you guys have done homework 6 yet, but there was actually, I believe it was in homework 6, a question that is related to this question where you had to prove that if the square of every element in a group equals the identity, then the group is abelian. And so I can actually prove that A and B commute with each other, even though it's not at all obvious that they do. So the first thing you want to do here is note that since A squared equals 1, if I multiply both sides of this equation by -1, then I get that on the left side I combine the powers and I get that's A to the 1, and then on the right that's A to the -1. So A equals A inverse. And then likewise, because B squared also equals 1, B also equals B inverse. And then the same for AB, because AB squared equals 1, that means AB equals AB inverse. So you can do the same equations and simplification with those elements. Okay, and then so what you note from there is that we know from the rules of how inverses work just in general that AB inverse is also supposed to be B inverse A inverse. When you distribute the inverse, the order of the elements reverses. So that means that since we have this equation and we have this equation, that means that AB equals B inverse A inverse, since both of those equal AB inverse. And we also know that B inverse equals B and A inverse equals A. Okay, so basically what we've found is that A and B commute. So we don't really have to make all of these huge lengthy lists of all the different products and powers of A and B, because A and B commute with each other. So there's not going to be that many different ones. So we really only have to worry about the powers of A, the powers of B, and then we could have things like, so basically V is just going to be like A to the I, B to the J, where I and J are integers. Okay. But even then, we still don't really have to use that many of them because we know that, for example, A is its own inverse, so we don't need any negative powers at all because all of the inverses are just given by the positive powers. And then we also know that A squared is 1. So really all we have is just these elements. We have 1, we have A, we have B, and we have AB. And that's it, because you don't need any higher powers, because once you start squaring them, it just comes back to being 1. And then we don't need any negative powers either, because, for example, A inverse is A to the negative 1 is A. So they just come back to being positive powers. So this is the whole group. It's just 1A, B, and AB. Although that's far from obvious from the presentation. Okay, so now that we have the whole group and we know it's just those 4 elements, we can make the operation table. So let's just do that. So this will be multiplication. Oops, not A first. Let's start with the identity. Okay, so this will be 1A, B, and then AB. And then this will be 1A, B, AB. Okay, so 1 times 1 is 1, and 1 times A is A, and then actually on the identity row and the identity column, you could just copy these over. Okay, so A times A is going to be A squared, which is equal to 1. And then let's see, A times B, if that's just going to be AB. And then A times AB, so A times AB equals A squared B, which is just going to be B because A is 1. Okay. And then B times A, so we already found that the group A and B commute with each other, so this is AB. And then, so let's see, B times B is going to be B squared, which is 1. And then B times AB. So we found that A and B commute with each other, remember? So this is going to be A times B squared. B squared is 1, so this is just A. And then AB times A. So again, A and B commute. This is A squared B, or just B. And then ABB. So B squared is 1, so this is just A. And then finally, AB times AB, we were told in the group presentation that that equals 1. Okay, so that is the operation table. Okay, so let's go ahead and look at part C here. So they've given us explicit definitions for what A and B are, and then they want us to demonstrate that the group generated by A and B under the matrix multiplication operation is actually the same, or is an example of a group with this presentation here. So all we really have to do is verify this, these equations here, and then it doesn't matter what A and B are, they were never defined in the presentation to begin with. So instead of 1, we're going to use the identity matrix. So this will be 1, 0, 0, 1 instead of 1, because we were assuming that 1 was the identity element. Okay, so we just have to verify that equation, or those 4 equations. So let's go ahead and do A squared, and just confirm that it's the identity. So this will be negative 1, 0, 0, 1. Times negative 1, 0, 0, 1. Okay, so hopefully you remember how to multiply matrices. We do the dot product of this row and this column. So negative 1 times negative 1 is 1, plus 0 times 0, so that'll be 1. And then we do this row again in this column here. So that'll be negative 1 times 0, plus 0 times 1, so that's 0. And then this row and this column. So that'll be 0 again, and then this row and this column, so that'll be 1. So we do get the identity. Right, and then we just have to verify this for the rest of them. So B squared, so that'll be 1, 0, 0, negative 1, times 1, 0, 0, negative 1. And that is, again, going to give us the identity. And then we have to verify what AB squared is. So let me just do AB in parentheses first. So this will be 1, and then 1, 0, 0, negative 1, and then I'll square that the end. So if we multiply those two matrices, let's see, we get -1, 0, 0, and then -1 again. So that is actually, that's -I. So if I square that, I do get I. Okay, so yes, this is a group with the presentation indicated in the angle brackets there. Okay, so investigation 25, the symmetric groups. So focus questions here. What is the permutation of a set? Under what operation does the collection of permutations of a set form a group? What are the symmetric groups? What notation can be used to represent elements in the symmetric groups? What is the cycle decomposition of a permutation and how can we find it? What is a transposition and why are transpositions important? What is the alternating group and what important properties does it satisfy? So let's get right into it. Okay, so firstly, what is a permutation? So permutations are special types of functions that are going to allow us to form an important family of groups. A permutation of a set, the way you want to think of it is just like a rearrangement of the elements of the set. Like you just scramble the elements of a set and put them back in some order. And then we use a function to keep track of the rearrangement. So the technical definition here is that a permutation of a set S is a bijection F from S to itself. And so just to remind you what a bijection is, because we had done that not too long ago in the Appendix A material. So a bijection is a function that is injective, meaning that every input has a different output, and it is surjective, meaning that every possible output is reached by some input. Okay, so bijection means every input has a different output, and every possible output in the codomain is reached by some input. So a bijection from a set to itself is a permutation. Okay, so let's do a preview activity here, and I just put the definition at the top to remind you of it. So go ahead and try this activity, pause the video, and try this, and then we'll go over it. Okay, so let's go over the answers here. I think it's not too complicated. So let S be a set. If we compose two permutations from S to S, is the resulting function a permutation? So the answer here is yes, it will be a permutation. So if F from S to S and G from S to S are bijections, we had a theorem in Appendix A that tells us that F composed with G is a bijection as well. And furthermore, it will go over the same domain and codomain. Okay, so it'll have the domain of S and the codomain of S as well. Okay, so part B, let F from S to S be a permutation. Does F have an inverse? F inverse? How do you know? So the answer is yes. All bijections have inverses. So they all have inverses. And then part C, if your answer to B was yes, is F inverse also a permutation? So again, I'm just referring to the material in Appendix A. Yes, the inverse of a bijection is a bijection. And if F goes from S to S, then F inverse also maps from S to S. Okay, so that's that. And now let's review permutation notation. So remember that when we investigated symmetries of regular polygons, we used permutation notation to write the symmetries compactly. I don't think we did this in the last investigation, but we did it back in investigation 19. So there's two ways to think about this notation. You can think about it geometrically, or you can just strictly think of it as function notation. So when you're thinking about the notation geometrically, the top row is the points, you're thinking about that point being moved somewhere. So like for example, if you look at the point 1 and you look at this counterclockwise rotation here, 1 is going to be moved to where 2 was originally. So we would put 1 in the top row and then 2 would be in the bottom row because 1 is moved to the original position of point 2. And then for another example, 2 gets moved to the original position of point 3. And then 3 gets moved to the original position of point 1. Okay, so that is how that notation works. And then if you want to think of the notation as representing a function, then you don't really have to have any knowledge at all of the geometry. You just have the input is in the top row and the output is in the bottom row. So if you put 1 into the function, you get out 2, put in 2, get out 3, put in 3, get out 1. Okay, so that's how that notation works. Okay, so regarding symmetries versus permutations, symmetries are examples of permutations, but permutations are not necessarily symmetries. So for example, let's look at these two examples. So here, this is the symmetry of a square. So this would be counterclockwise rotation by 90 degrees. So if we had this little square here and we had 1, 2, oops, I think I have to label them in counterclockwise order for this to work. So 1, 2, 3, 4, and then I give it a counterclockwise rotation. So every vertex is moved to the position that is 1 greater than it, then that would be this permutation here. But on the other hand, over here, this is not a symmetry of a square. And so the reason you can tell that, so think about what that square's going to look like if we apply this permutation to it. So 1 would be moved to the position, the old position of 2, and 2 would be moved to the old position of 4, and then 3 would stay the same, so it would stay where it's at, and then 4 would be moved to the old position of 1. What kind of transformation is that? That's not a symmetry. Like, you can do that to a square, but you're going to rip it up in the process. So that would not be a symmetry. So symmetries and permutations, they might just seem like cool things to do, but they actually have a ton of applications throughout the sciences, everything from molecular chemistry to genetics to quantum mechanics. So they are fun and they are useful. Okay, so now let's think about the symmetric group of a set. So this activity, together with preview activity 25.1, is going to verify that the collection of permutations of a set is in fact a group. So go ahead and give this a try, and then we will go over it. Okay, so let's go over the answers here. So y is the identity function from S to S, a permutation of S. So the identity function from a set to itself is always a bijection. I mean, I think that should be pretty clear, right? Like, different inputs always give you a different output, and you'll reach every possible element in the codomain because it'll be identical to some element in the domain if you're going from a set to itself. Okay, so that will be a bijection. So that means it's a permutation. And then y is the composition of permutations on S and associative operation. So this one is equally kind of simple to understand. Function composition is always associative. Yeah, function composition is always associative. I think we had talked about that earlier in the class. But if you think about it, try to do something like this. F of G of H, and then apply that to X. What are you going to get? So you're going to get F of G of H of X. And then what is that? It's just F of G of H of X. And then if you try to do it the other way around, so let's see, F of G of H of X, you'll get the same result. So this is going to be F of G of, so it's so hard to write this function composition notation. Like that. So this is just also going to be f of g of h of x. So function composition is always associative. And then finally, part C, explain how the results of this activity and preview activity 25.1 establish the following theorem. So the theorem is let S be a set, and let P of S denote the collection of permutations of S. Then P of S is a group under the operation of function composition. So the four properties of a group are it's closed under its operation. Sorry if you guys can hear my cat squeaking in the background. He's a very squeaky little fellow. So we showed that we showed in the preview activity 25.1 that the permutations were closed under composition. And then we also need associative, and we just showed that just now. We need inverses, and we showed that just now. And then we need the identity. Oh, sorry, the inverses we did, that was in 25.1. But anyway, we've got all parts. So the set of permutations is in fact a group. Okay, everybody, thanks for watching, and we'll resume with investigation 25 last time. So if you have any trouble with your homework, or you need any help, or you just want to talk to somebody, I'm happy to talk to you guys. Just send me an email, and we can email or we can talk over video chat. And I will see you next time. Bye-bye.